Okay, so we're going to talk about projectile motion from a height up here, landing at a place down here. Okay, a couple different things. One, if we have a projectile that's launched here and it lands here, in other words, if y1, the height of the first thing, height 1, is equal to height, well, we could say height initial and height final, or y1, y2. If these are equal, then there's a range formula for this, okay? And the range formula for that is v initial squared times sine 2 theta all over g. And so theta would be the angle here, and v is the entire velocity. It's not made up of the horizontal and the vertical, it's the entire velocity in v initial squared. So v initial squared times sine of 2 theta over g will give you the range from here to here. Okay? Everybody follow that? Now, I said that so I could say this. That's not what we're going to do. So we're going to go from up here and we're going to land down here. So you can see, obviously, y1 and y2 not equal. Okay? So that formula is no good for this situation. Good for that situation where y1 and y2 are equal, like a punter, like if in NFL, college, whatever, high school, you punt, and then it lands on the same height. That's perfect for that, but not this. Okay, just needed to throw that out there. All right, so this thing we're about to do is we're going to launch a projectile launcher from up here, and you're going to get a very specific angle. I'm just going to put theta in there for now. You each are going to get a specific angle, and we're going to launch it at different angles so that we get different ranges. Okay? So what we need is the velocity coming out, and then we need to break that into horizontal and vertical velocity. Let me stretch this out so it actually matches. Okay, so the velocity here is made up of a horizontal component and a vertical component. The vertical component coordinates with the amount of time it's in the air. We need the vertical only to determine the time of flight. The horizontal then, multiplied by that time, will give us the range. So the range is equal to the horizontal velocity times the time is in the air, right? Distance is velocity times time. Okay, so our range, we're going to determine wherever that range length is, the distance. Okay, so the range is going to be horizontal velocity times time, because what do we know about the horizontal velocity?
Constant.
It's constant, right? So that's why we can use the constant speed formula. Now, vertical v initial is the opposite side of the triangle that makes up, or right triangle that makes up our two component vectors, right? The horizontal is the adjacent side. C and S for sine and cosine. So opposite is equal to V times sine theta. Okay? Adjacent is equal to V times cosine theta. Right? So we determined the velocity, the exit velocity of the launcher last time, and we'll reestablish that before we go. But we're going to establish for certain what is that exit velocity of the launcher. So we can use that here. The exit velocity times sine of your angle, because each of you is going to get your own angle. Okay? Once you get that, that is equal to your initial vertical velocity. Now, height final is equal to 1/2 gt squared plus v initial t plus height initial. What did we figure out our height was? I think we measured our height 4.92,
yeah,
right?
5 meters.
So our height that we had up here was 4.92 meters up to the projectile launcher down to the floor.
We can't round to 5?
We won't do that today.
Okay.
But yeah, rounding to 5 wouldn't be out of the ordinary, because especially we're talking 8 centimeters. That's, you know, that much, whatever. Anyway, So our height final is 0, and what's nice is this puts this in quadratic form. Half of g is negative 4.9 t squared plus v initial. What's our v initial? V times sine theta. So we're going to put v times sine theta t plus height initial. And our height initial is 4.92. 4.92. So quadratic, a equals negative 4.9. B equals v times sine theta. Right? V is the exit velocity of the projectile launcher.
Mm-hmm.
What happened to the 1/2? Like, why didn't it get carried down?
What's half of g?
Oh.
Negative 4.9.
Oh, it just happened.
Because g
1/2.
is 9.8.
Okay.
Half of g is 4.9. That's why I put negative 4.9 there. Half of g is 4.9. Good?
Yeah.
So I just threw it in there, right? It's in the soup. Okay, so now b is v sine theta, and c is your original height. So t is equal to negative b plus or minus the square root b squared minus 4ac. My brain's going way ahead of myself here. 4ac all over 2a. What's 2a? What's a?
4.9.
Half of g. What's 2 times half of g?
Oh, not negative 9.8.
G. Alright, so 2a is just g,
What I said.
right? So this is all over g. Does it look kind of familiar, that other? Where I had v squared times sine 2 theta all over g. Weird, right? So negative b, negative your vertical velocity, v sine theta, v times sine theta, plus or minus square root of, what's b? V sine theta. V times sine theta. That whole thing squared minus 4a. Isn't that like 2g? 4a is the same as 2g.
Mm-hmm.
2g. And then what is c? Your initial height, 2gh. Right? So far, so good? What do we know about g? Positive or negative?
Negative.
It's negative, so we're subtracting a negative. Does that make sense? So we're not going to have a negative number under there. There's no way, because we're subtracting a negative, so it's got to be positive. Make sense? So then you're just going to plug this information in to get the time in the air, your time of flight. Okay? Now, once you do that, take your time of flight, multiply it by v cosine theta, and this is your horizontal velocity. So v cosine theta times t equals the range.